Hi, this is Sherry Shabowski, and today we're going to talk about the control of blood sugar. The pancreas is an exocrine and an endocrine organ. The endocrine component is responsible for maintaining a constant and adequate amount of glucose in the blood. Glucose plays a critical role in energy production for every cell in the body. Therefore, maintaining appropriate glucose levels is a critical function. If the level is too low, the brain is the first organ to shut down. We absolutely need our brains firing on all cylinders, so we need to make sure the supply is adequate. If the glucose level is too high, especially if it's chronically elevated, it is like having syrup circulating in your vessels. Chronic hyperglycemia damages small blood vessels, resulting in numbness and tingling in the hands and feet, sometimes no sensation in the hands and feet, which lead to sores on the feet. It also results in renal damage or kidney damage, and it can cause visual loss. And that's just to name a few things. It also provides a food source for bacteria and fungus, so infections can spin wildly out of control. Thank goodness we have a pancreas to keep glucose levels consistent. The alpha cells of the endocrine pancreas make glucagon. Glucagon acts on the liver to increase circulating glucose when the levels are low. The beta cells make insulin. Insulin reduces blood sugar levels by interacting with cell receptors and opening a door in the cell membrane so glucose can come in. This is most important after a meal is ingested. If the glucose goes into the cells to provide the energy they need, it means glucose moves out of the blood, so circulating glucose levels will go down. When glucose levels are high, the pancreas releases insulin, which facilitates the movement of glucose out of the blood and into the cells. When the glucose goes into the cells, the circulating blood glucose goes down. If the blood glucose is too low, the pancreas releases glucagon. Glucagon acts on the liver in two ways. It stimulates glycogenolysis. Glycogen stores are converted into complex carbohydrates in this process. It also stimulates gluconeogenesis, which uses other sources of energy like amino acids and glycerol to make glucose. So, low circulating blood glucose levels cause the release of glucagon, which acts on the liver, resulting in increased blood glucose levels. These are balancing hormones. As I said earlier, insulin basically opens the door for circulating blood glucose to move into the cells so they can make energy. In type 1 diabetes, the immune system makes antibodies to the beta cells in the pancreas. Now there will be no insulin or very little insulin. When blood sugar levels go up, there is no way to decrease it. Worse than that, there is no there is no one to open the door for glucose to go into the cells and feed them. Even though the circulating blood glucose levels can be very, very high, the cells are still starving for glucose. The door is not open and none can get in. So, where are we? Well, the person is diabetic. The blood sugar is high. There is no insulin. The cells are starving for glucose and in desperate need of ATP, especially the brain cells and the muscles. We already know that our cells need two essential substrates, oxygen and glucose, to make the energy necessary for bodily functions. We already know that when oxygen is not available, the cells shift into anaerobic respiration. The amount of ATP that is made is reduced by 94%. But there are two substrates. And in this section, we want to know what happens when there is insufficient glucose. Well, this is ketogenesis. It starts with glycolysis. But in the case that there is no glucose, They need a workaround to make energy. As you see from this picture, the first thing that happens is oxaloacetate that is already made can leave the mitochondria and be converted into glucose. This is called gluconeogenesis. This works for a while, but then it runs out. In the second example, we have triglycerides. They are broken down into glycerol and fatty acids by way of lipolysis. Glycerol is converted into pyruvate, which moves into the Krebs cycle or citric acid cycle, where it is converted to acetyl-CoA. Fatty acids are converted into acetyl-CoA in the mitochondria. Excess acetyl-CoA is converted into ketones, like acetone, acetoacetate, and beta-hydroxybutyrate. These ketones provide an important energy source that replaces glucose for muscles and the all-important brain cells when the glucose is insufficient. The downside is that all the backup mechanisms have byproducts, and they typically are not great for the body. In this case, the ketones are acidotic, and if there is enough in circulation, they can make the blood become significantly acidotic, which is dangerous. The process keeps everything going, but at a cost. One of the axioms of pathophysiology is that when a function is crucial, the body will adapt with backup mechanisms in place to make crucial functions keep going. Again, spoken as a true ER doc, there is always a price to pay for emergency services, and in this case, it is the potentially dangerous byproducts. This is the story of diabetic ketoacidosis. If you like this content, please check out the Medical Education in Minutes Facebook and YouTube content. Please like and subscribe. I would really appreciate it. There are also full courses on the medicaleducationinminutes.com website if you're interested in something like that. Thank you for learning with me, and I'll see you next time.